In this tutorial, we're going to calculate how much power and work are needed to keep a sled moving for 5 minutes across the ground. So here's the ground. The scenario is a parent is pulling a child on a sled like so, and we're given information about the angle at which this rope is oriented relative to the ground. It's 42 degrees up. We're also told that the sled is moving at a constant speed of 1.1 meters per second directed to the left. The parent is exerting a constant force on the rope, which in turn exerts a constant force on the sled of 34.0 newtons. Now we know immediately that that's not the net force on the sled. The net force on the sled must be zero because it's moving at constant speed, but what we're interested in doing is just analyzing the power and work associated with that particular applied force, regardless of what other forces are acting in the system. We also know that this entire process is occurring over a time interval of 5 minutes. We have an equation relating power to force and velocity. We also have an equation relating power to the change in energy over time. We'll use both of those. Let's clear some of this ice and get started. So we'll start by calculating the power, which is just equal to F dot V. Now there are multiple ways to analyze dot products, but by far the most straightforward choice in this case is just to calculate the magnitude of F times the magnitude of V times the cosine of the angle between them, because we're given all three of those things. So we plug in values, 34 newtons for F, 1.1 meters per second for the speed, and then put in 42 degrees for the angle, and we find that the power is 27.79 newtons times meters divided by seconds. Well, a newton times a meter is a joule, and a joule per second is a watt. So this comes out to be 27.8 watts. Since the force, velocity, and angle are all the same for the entire 5 minutes, that's actually constant power that's being exerted by the parent to pull this sled. Okay, so we figured out the power. What about the work? Well, to do that, we'll use the equation P equals dE dt, and let's rearrange this by multiplying both sides by dt. Mathematicians, cover your eyes for a moment. Of course, this becomes okay as long as you put integral signs in front of it. Alright, so the integral of P dt equals the integral of dE. Well, we just said that the power is constant for the entire time interval, so we can pull P out of that first integral and write that P times the integral of dt equals the integral of dE. Let's make a little more room. Now, even on a bad day, I can handle those integrals. The integral of dt is delta t, the integral of dE is delta E. And actually, if you look at this result, you probably would have been willing to believe that just from the fact that the power was constant and is equal to dE over dt, right? Because if the power is constant, you could change dE dt to be delta E over delta t and get out this relation. But we did it the slightly more rigorous way by integrating. The question is what to do with this delta E. Well, if you think about it, the only two things that can change the energy of a system and generate a net delta E are work and heat transfer, and in this course we're trying our best to avoid heat transfer, so it must be the case that delta E for this particular problem is just the work. So P delta T equals the work, therefore we can put in our values for the power and the time interval. The power, using a little more precision, was 27.79 watts, the time interval was 5 minutes, which we should convert to seconds so that we get out sensible units for the work, and we get that the work is 8337 watts times seconds. Remember, a watt is a joule per second, so that gets us back to joules. The work is 8.34 times 10 to the third joules. Now you might see that number and think, wow, this person was really a powerhouse. They exerted over 8,000 joules. Well, actually, a joule is a pretty puny unit of energy. If we wanted to relate this to English units, that corresponds to something like 2 calories with a capital C. So they've exerted some energy, but maybe not as much as the number 8,000 would suggest. One other detail. The parent really did do over 8,000 joules of work on this sled, so where did all the energy end up? Well, clearly it didn't go into speeding up the sled because the sled was moving at constant speed for all 5 minutes. The most likely suspect is that, simultaneously, friction was doing work on the sled, but actually doing negative work, meaning that it was taking energy away from the system. So all of the energy that the parent would have added to the system was simultaneously going away through friction, probably into something like a combination of heat and sound.